All right, so I just want to finish up this chapter. And at the end of the chapter 15, we talk about angular momentum. So if linear momentum is just the mass times the velocity, angular momentum is a measure of momentum, but it's always relative to a particular point. So, so as your book says, it can be thought of as the moment of the particle's linear momentum. You could also think of it at some level as a rotational equivalent to linear momentum, because often once we get away from the idea of a particle, we might be thinking about the rotation of an object. And so because it's rotating, of course, it has a motion, and we would still think of it as having momentum, but it has a particular momentum because of rotation. So those are just some ways that we can think of angular momentum. Going along with the idea of how we define it as the moment about a point, we define it using the cross product, which should make sense because moment of a force is r cross f, so angular momentum, which can be the moment of momentum, is r cross with the momentum. And so here we see the definition of angular momentum about some point. Notice also, because the magnitude of the angular momentum would be r times mv times the sine of theta, which would be between r and v. It ends up that that quantity could be thought of, or that distance, if we pair the radius and the sine of theta, we could just think of that as sort of like a moment arm, and we can write the angular momentum in this way, as the momentum times the moment arm. In any case, if we go with the idea that angular momentum is like the angular equivalent to momentum, we might sort of think about the fact that when we learn about angular quantities, we see that there's oftentimes rotational equivalents to it, to our linear quantities. So, for instance, we say a moment is a force that causes a rotation. So moment is like the rotational equivalent to force. And we just introduced this idea of angular momentum, and the angular momentum is like the rotational equivalent to momentum. So we might sort of hypothesize that for a rotational equivalent to Newton's second law could be that the moment can be expressed as the time derivative of the angular momentum. So we've just replaced linear quantities with rotational quantities. And so we want to say, well, is this true? I mean, you can't just like guess and then go with it and say, well, it must be because it seems like it makes sense. We have to prove it. If we take the definition of the Newton's second law, and we want to sort of modify this to look like this proposed expression, we realize that we could actually get the moment if we take r cross f. And then, so let's say we're going to do that to the entire equation. So we get r cross f is equal to r cross dp dt. And so I know that I kind of changed this. Remember that this is the derivative of momentum with respect to time. And just remembered that in our book we use L to represent momentum. So sorry about that. Okay, so is this true? Well, is this equal to the time derivative of angular momentum with respect to time? Well, let's find out. Basically, I want to know if this is equal to this. So I'm going to look at angular momentum is r cross mv. So let's look at what the time derivative is. So I took the time derivative of angular momentum. Now, when I did that, I started with this definition of angular momentum, and I took the derivative with respect to time of each term. But one of the things that I didn't do, I used the product rule, but we're letting mass stay constant, so I never took the derivative of mass with respect to time. And if we sort of compare what I have here to this, because I want this to be equal to the derivative of angular momentum with respect to time, it would be true if this was 0. And so we have to ask ourselves, why would this be 0, this first term? Notice it's v cross mv. So I would be taking the cross product of two parallel vectors, which indeed is 0 because they're parallel. The angle between them is 0, so the cross product would be 0. So it actually is true. Our sort of conjecture that we started off with was that the moment due to a force could be equated to the change, the derivative of angular momentum with respect to time. So this actually is true. Yes, it's true. Okay, so once we do that, we can actually come up with an angular impulse equivalent to what we did with regular momentum. So had more room there. So if we rearrange this expression, or we take this, and we can rearrange this and have the sum of the moments over time is equal to dh, and we integrate that, we can have this as h2 minus h1 is equal to this. And so this is like the angular impulse, and this is equal to the change in angular momentum. So this idea that we can sort of have all these angular equivalents to our linear relationships really seems to be holding true. And what it's telling us here is that the way that I can change angular momentum is to exert a moment on the system for a certain amount of time, and that will cause a change in angular momentum. There are cases, of course, where we have conservation of angular momentum, and one of the classic examples of when angular momentum is conserved would be when your moments or your impulse is 0. This is actually true for what we call central force problems, because in those cases the only force that's acting is parallel to the r, which would give a moment of 0. And a classic example of a central force would be gravity. And so that's one of the reasons that we say when planets are orbiting the sun, they experience a conservation of angular momentum, because that force of gravity does not exert a moment. And so because of that, the angular momentum is conserved. And so here's a picture of a satellite. Gravity is the central force. The angular momentum will be conserved because the net moment acting on the satellite is 0. Therefore, the initial angular momentum is equal to the final angular momentum. So again, we're using the fact that the moments integrated over dt is equal to the change in the angular momentum. If this is 0, angular momentum remains constant. So let's look at an example of a problem where we could use the angular impulse angular momentum relationship. So we have these two spheres are on a rod and they're able to rotate in the plane of the page. And there are two things that are happening here. There are two forces of 10 newtons acting on the masses, and then there's also a couple moment that depends on time. And we want to know if everything starts from rest, what would be the speed of the spheres after 4 seconds. So what we're going to do is we're going to look at the impulse momentum relationship. And so the sum of the moments acting on this system integrated over time is equal to the change in the angular momentum, but we're going to start from rest, so the initial angular momentum is just 0. Now we have two different moments acting on this system. First we have this time-dependent couple that depend 8t, but we also have these two forces. These also could be thought of as a couple. The moment that they would produce, I'm going to call it moment of the couple, would be equal to the force times the distance between them, which is just 1. And so we have to add to this 10. So that is the total moments acting on this system. And that's going to be equal to the final angular momentum. And we're going to let this go for 4 seconds. So if we integrate this, we get 8t squared over 2 plus 10t evaluated at 0 and 4. Let's just simplify that. We get 4t squared plus 10t evaluated at 0 and 4. And this actually ends up to be 4 times 16 plus 40, and that equals 104, and that's equal to the final angular momentum, which would be that you have two masses times their velocity times their radius. And so the mass is, each of the masses are 10 kilograms. I had to look, I forgot. The velocity is what we're looking for. And the radius is 0.5. And so if we solve for velocity, we end up with a final velocity of 10.4 meters per second. And so that was a simple application of the angular impulse expression. So that finishes the chapter for us. We'll see you next time to do some problems.